Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay. Hi, I'm Tom Ball, and welcome Monday morning talk. We have Sanjit Seshia visiting us from Carnegie Mellon University. He's a graduate student there finishing his PhD under the supervision of Randy Bryant. And he's going to tell us today about using Boolean methods for reasoning about reliability and security.
Thanks, Tom. I'll be speaking today about using techniques for Boolean reasoning, such as Boolean satisfiability solving, in building analysis tools for reasoning about computer reliability and security. The work I'm speaking about today is joint with Randy Bryant, my advisor at CMU, as well as with collaborators at Wisconsin and CMU, and as well as Intel. The cost of computer systems failure can be enormous, and here are some of the well-known examples in the recent past. I guess I'm at a place which has done a lot of research in this area, so it's a bit of preaching to believers, I guess. But let me just put out one statistic, which is the NIST did a survey a couple of years ago, and the result was they estimated the cost of software bugs to the US economy every year to be of the order of around $60 billion. So clearly there's a problem here, and it can be solved using multiple techniques at various points in a product's lifetime. And ideally, what we'd like to do is catch errors and correct them as early as possible in the design process. And what I've been working on for my PhD work is in static techniques to catch errors in software as well as hardware systems. In particular, I've been working on a class of techniques based on so-called formal methods. The general idea here is that we build a system, an automatic tool, that takes in two inputs, a system description like source code or RTL in the case of hardware, and a property of interest. And we'd like to check if it's either safe with respect to the property or if there's an error trace. And there are two aspects to any such tool. There's the modeling aspects, which is how do we take source code and generate a formal model in logic. And then the automated reasoning aspects, which is techniques like model checking for proving whether the property is satisfied or not. And one instance of this modeling technique, this class of methods that's been very successful in the last 10 years, including work right here at MSR, is to model systems using Boolean state and try to prove control properties of these systems. So the formal models tend to be things like finite automata or Boolean programs. That was done here in the SLAM project a couple of years ago. And then reason about these using techniques like model checking based on Boolean satisfiability solving or data structures like binary decision diagrams. These techniques have been very successful in reasoning about control-related properties, like protocol verification or checking usage protocols of API. But so far, they haven't proved their use in analyzing properties that have a lot of data, in which you have to reason a lot about data or timing in addition to control. And that's the space in which I've been working on. So I've been looking at reasoning about systems modeled as they are, using infinite state models with richer data types like integers, reals, basically model systems as they are in programs or in hardware. And then reason about these systems using first order or even higher order logics. Specifically, I've been working on building decision procedures for first order logics involving arithmetic. And there are two main ideas in the work I've done. First, we'd like to leverage all the work on Boolean reasoning that's been done before and which has proved quite successful in the methods that I described in the previous slide. But also, we'd like to exploit domain-specific problem structure. And I'll make both of these ideas very concrete in the rest of this talk. On the applied side, I've built two systems. One of them is a verification tool called UCLID, which was jointly started with my advisor as well as Shubhendu Lahiri, who's here at MSR now. This is a multi-purpose verification tool. It can be used for a variety of verification tasks. I have applied this to both software analysis as well as hardware verification. So in the software space, I've been looking mainly at security properties. The first is detecting viruses and worms, and I'll speak a little bit about that work in this talk. And the second is finding format string vulnerabilities and generating tests that exercise these vulnerabilities. The other work that I've been involved with at CMU is in hardware verification. That's verifying high-level microprocessor designs, and that's something Shivendu has done a lot of on as well. This tool is publicly available. It's been used outside my university in both research as well as in teaching. Another tool I've built, which I won't get a chance to talk about today, is a model checker for timed systems called TMV. I've applied this to verifying self-timed circuits, which are asynchronous circuits that operate under certain timing assumptions. And one of the main case studies we did was to analyze a published version of a circuit that's in the Intel Pentium 4 integer unit. And we actually found an error that turns out to be a power consumption problem. So if you'd like to learn more about this work, I can talk to you about this after the talk. And I think this, in the context of software, this can be extended to things like embedded software or even distributed systems that operate under timing assumptions. Yep.
So coming back to a couple of slides ago, wondering, yeah, in those infinite state models, do you handle dynamic memory creation in any of your?
Not in my work.
Okay.
Yeah, so the logic hasn't been extended to handle heap data structures. Yeah.
I think it's a very interesting question whether Boolean methods can be
right.
made.
I think that's sort of the next step in saying, can decision procedures be extended to reason about heap data structures? Okay, so here's the outline of my talk. I'm going to begin with a motivating application that's malware detection, detecting if a given binary is exhibits malicious behavior that's captured in a signature that's in a virus database. And then in this talk, I'm going to mainly focus on how decision procedures are used in that detection work. So the main part of my talk is going to be on how do we build decision procedures based on Boolean reasoning tools. And I'm going to illustrate this for a specific logical theory that's called Quantifier-Free Presburger arithmetic. And then I'm going to go back and revisit the motivating application as well as talk about some other applications and contributions. And I'll end up this talk with some directions for future work. Okay, so here's the problem. On the left-hand side, we have the code for an original virus, and say this is something we know is already a virus. It's in our database. And on the right-hand side, there's a fragment of potentially malicious new code. And it turns out that virus writers often take the code for original virus and change it just a little bit by adding doing certain code transformations such that escapes detection by commercial tools. And it turns out that even very simple obfuscations fool the current virus scanners. So according to a recent study by Christopher and Ja, just published last year, the false negative rate, that is the number of such variants that escape detection, can be quite large, of the order of over 75%. So clearly this is a problem, and the main problem with current tools is that they're syntactic. They're based on pattern matching or regular expression matching, and it's quite easy to fool them. So let me just talk about this example I have here up on the slide. This code over here on the left has been obtained by doing fairly simple transformations, like inserting this sequence, which essentially amounts to the second, third, and fourth instruction, which amounts to a no-op, and then by inserting jumps in the code that change the syntactic look of this code, but don't really change the control flow.
So do the commercial antivirus software vendors, do they actually tell you how they do their checking? I mean, have they published how they do analysis for code variants?
I don't think that it's published in like one place, but people have given talks, so what they do is essentially look for interesting strings, for instance, or build up to deal with simple no-ops. They build up a little state machine where you ignore a no-op and just look at the relevant code, but basically you just do syntactic pattern matching. So the essence of many of this tools is that they really do regular expression matching, and for more I guess there's a class of tools which actually do emulation. So it's like runtime detection of viruses. Maybe. All right, so what we've done is to take a semantic approach to model x86 program semantics explicitly, and then use a combination of data flow analysis as well as theorem proving for a quantifier-free subset of first order logic. Of course, this problem is undecidable. It's a question of program equivalence in general. But our approach is targeted towards catching common obfuscations that happen in practice, and it's targeted towards making it harder for malware writers to escape detection. So I won't have time in this talk to present our algorithm in general. What I'm going to do is just talk about the part in which we use decision procedures. And I'll do that by speaking about a common obfuscation technique that's used, which is the method of using semantic no-ops. Okay, so on the left we have the code for the original virus I showed you. On the right-hand side, it's essentially the same code, except in pink there's a sequence of instructions that's been added in, and that's essentially a no-op with respect to the state relevant to malicious behavior. So with respect to the registers that are used on the left over there.
So how do you define the state relevant to malicious behavior?
That's a good question. So that's sort of the core of how you define your signature. So what we do is we start with a code fragment that someone manually has identified to be malicious. Then we do some simple transformations to simplify the code, like constant propagation. Once we do that, we rename the registers, make them generic, and so that becomes the signature. Okay, and then we consider every instruction in the signature to be and every register that's mentioned to be relevant. Okay, and the general idea is every instruction in the signature should match some instruction in the new binary, and then there's other stuff. And one of the classes of that other stuff is to have these kinds of no-ops, but the algorithm is more general than just looking for these.
So would that be the way the syntactic approaches also work? They sort of define kind of the core.
Yes, yeah. They look at the core. Actually, what the core is tends to vary quite widely. So it could be just something as simple as just a string, like some SMTP message that's sent out by that one, or it could be as complicated as the entire binary itself. So what we found in our studies is that the signatures does vary over this whole spectrum. So for instance, both of these examples I gave you don't have very good generalization ability, right? And so that tends to be the problem with all of these tools.
So in your approach, it's possible to get false negatives, that you actually identify some code as being malicious while it actually isn't?
False positives, I would say. So our current implementation is biased against false positives. But we did a false positive study, and we got no false positives in about 60 or so viruses and worms that we had tested. So, since our algorithm is biased against false positives, it's not that I guess not that relevant. I can tell you more about this afterwards. Okay. So so at this point, I'm just going to assume that we've detected which code sequences have to be checked for no-op behavior, and I'm going to tell you how that's transformed into a theorem that you have to prove. And I can tell you more about the exact matching process after the talk. Okay, so here's the sequence that I showed you on the previous slide, and the question I want to ask is this a no-op with respect to EAX, where EAX is the register that was used in the signature on the left? Okay. And now let me just tell you how we transform this into a expression in logic, a question in logic. So I'm going to call the initial values of EAX and EBX just subscripted by 0. So those symbols correspond to the initial values. And then I'll just transform this into something like static single assignment. Corresponding to the first instruction, the equality out there gives the relational semantics of that instruction. Now the middle three instructions here essentially swap the contents of EAX and EBX. But of course, in writing out the semantics, we don't have to know that. All we can do is just express them as bitwise operations. So in this case, this simply represents the results of taking XORing the value, all values of EAX and EBX and writing it to EAX again. And then the last two instructions can also be translated similarly. And so we get a logical expression at this point, which is the relational semantics of that straight line code fragment. And then the question we want to ask is, given this is what the code does, is the initial value of EAX equal to the final value of EAX? Yeah.
So this is a case where there's no effect on the state, on the external state of the program. But what if the code that's inserted isn't a no-op actually?
Right.
But it just doesn't affect the core state that the virus is trying to manipulate. It affects some other state.
Right. So then it would be a no-op with respect to the core state.
Okay. So that's all you care about.
That's all I care about. So that will be reflected in the equalities on the right-hand side here. Okay. So the question I want to ask is this Boolean expression true for all values of the variables it contains? Or in logical parlance, is this Boolean expression valid? Okay, so in this talk, I'm actually going to work with the dual of this question, which is satisfiability. So given a code fragment, I'm going to ask, is it not a no-op with respect to EAX? And that's asking if, taking the negation of the formula I showed you on the previous slide and asking if that's true for any combination of values to the variables it mentions. So in order to discharge these queries, we need a decision procedure that takes in an input formula, which is a Boolean expression over not just Boolean variables, but also integers, arrays, or in general some fragment of first order logic. And it outputs that either yes, it's satisfiable and the fragment is not a no-op, or no, it's not. So this is going to be the subject of the rest of the talk. How do we build these decision procedures? And specifically, what's my approach to solving this problem? So here's our approach. We start with an input formula, which is in subset of first order logic, and then perform a single step satisfiability preserving transformation to a Boolean formula, then pass that off to a Boolean satisfiability solver, and the answer that the Boolean satisfiability solver returns is the answer to the original problem. So the part that's highlighted in blue on this slide is where my contributions come in. And the Boolean satisfiability solver is just something other people write. So we just use off-the-shelf stat solvers. Okay. So natural question is, why do you want to use this approach? And the answer has two parts. First, it turns out the input already tends to be a SAT problem. And that's because interesting systems have a lot of interesting control. And that leads to several Boolean variables and operators. But secondly, there have been dramatic advances in SAT solving over the past 10 years or so. And in my experience, SAT instances with around 10,000 variables, and these are the primary inputs of the circuit, not counting intermediate variables, have been routinely solved just within a few minutes, or a few seconds, or at most within a few minutes. And so this is some technology that MSR has also leveraged in this group. So let me just point out a few features of our approach that distinguish it from other SAT-based methods. So the first is that we have a clean separation between the SAT solving part and the part that actually does the encoding. And what I found is that this separation allows us, of course, trivially allows us to plug in the fastest SAT solver. And it, in fact, we've been able to achieve orders of magnitude speedups by just doing that, replacing one SAT solver by another. Secondly, it's very easy to generate satisfying solutions to the original formula just by picking up the solution given by the SAT solver and mapping it back to the original first order types that the solution came from. Okay. So what I haven't told you about yet is what subset of logic is the input formula in, and secondly, how this transformation is done. Okay, so that's what I'm going to talk about in the next part of this talk.
Say again, what's the purpose of the transformation?
So the purpose of the transformation is it's just a strategy, right, to decide the original formula. That we transform into a Boolean formula and preserve satisfiability in the process.
Okay, what do you mean by strategy?
It's one way. It's one distinct procedure for the problem.
Okay, so you're already given a Boolean formula, and then you transform the formula in order to have a more effective way of deciding.
No, you're not given a Boolean formula. You're given a formula in first order logic, some subset of first order logic, and then you transform that to Boolean formula. Okay, so let me. Yeah, question.
What is the loop doing there? Could you go back one slide? If it's satisfying satisfiability preserving, then you don't need any iteration.
You don't need an iteration. This is not an iteration. It's just an input. So all I'm saying is that just preserve the mapping, right? So internally, the transformation preserves the mapping so that given a solution to the SAT formula, you can generate a solution to the original formula.
So the core problem here is to represent first order logic in propositional logic. Is that the core?
The core is to translate first order logic to propositional logic. Yeah.
Okay, and you don't do that iteratively.
We don't do it iteratively.
I see.
That's right. Okay. So let me say what the starting logic is. Okay. So on the right hand side on the slide, I have listed 4 logical theories that my tool handles. So the starting formula is in the combination of these theories. On the right hand side of the slide, I've listed examples of modeling that one can achieve with each such theory. So the first is quantifier-free Presburger arithmetic, which allows one to express integer linear constraints. So basically, one can express things like array bounds checks in this theory. The second is finite precision bit vector arithmetic, which allows one to express bitwise operations like we had in the x86 example. The third is a restricted subset of lambda expressions, which allows one to model data structures. So array operations, memory operations for hardware, data structures like queues, for instance. And then the fourth category is a catch-all for anything that isn't precisely modeled in the top 3, like for instance integer multiplication, in which case we just treat a function as a black box, and all that's preserved is the fact that it is a function, that it maps equal arguments to equal values.
The restricted lambda expressions, are they like higher order logic?
They're not higher order logic, so that's what they're restricted. It's like essentially mutable arrays.
I see. So when you say lambda expression, what should I think of it as functions?
You can think of it as functions, yes. So functions like a memory is a function from addresses to data to values, right? So,
question.
Yeah.
So are these choices based more on what you're capable of doing, or is it motivated by what you need to do to address, real examples?
Okay, it's by second what we needed to do. Okay, so in this talk I'm going to talk about the first theory and how that's translated to SAT, and I can tell you more about how we handle the others after the talk. So let me talk about, let me first start by giving you some background on this theory, quantifier-free Presburger arithmetic, and then I'll give the decision procedure in 3 steps. I'll start with the intuition about why we use this approach. I'll state the main theorem that the procedure is based on and sketch out the proof, and I'll end up with experimental results that show that in practice this procedure does very well. Okay. So here's the formal definition of quantifier-free Presburger arithmetic. A formula phi is either a linear constraint, a linear inequality, for instance, over integer variables, or you can build more complicated formulas by using the standard Boolean operators. Okay, and the decision problem is, given a formula phi in this theory, which I'll call QFP for short, is phi satisfiable? So geometrically, what that means is I have a union of polyhedra in Rn, and I want to find an integer point in this union if one exists. So this problem is NP complete, and it's easy to see why it's NP hard because you can very easily express SAT in it, but proving that it's an NP takes a little bit more work, and this is based on results that were obtained in the 70s So basically what one has to show is that if a satisfying solution exists, then there's one within a bound D where log D is polynomial in the input size. So geometrically what that means is that we have a box of side D near the origin, and if there's any integer point in the union of polyhedra, then there better be one inside that box. So, so this problem might seem quite familiar to you, and that's because it's a combination of two very well studied problems: integer linear programming, which I call ILP, and Boolean satisfiability. So the general strategy that's been employed so far to decide this problem is to combine ILP and SAT. So for instance, suppose this was the input. So your input formula can be viewed as a Boolean circuit where the leaves of the circuit are linear constraints. And so the standard approach is to first ignore the linear constraints, treat them as Boolean variables, and then come up with some satisfying assignment to the leaves of the circuit that make the output true. And suppose that the one on the left was the satisfying assignment. Then this satisfying assignment induces a certain set of linear constraints. So if a constraint, for instance, is assigned false, we flip the sense of the inequality. And just putting together that set of linear constraints, we get an integer program. If you solve that, and if it's feasible, if you get a solution, then we're done. If not, we have to find a new satisfying assignment to the leaves of the circuit, and then repeat the process. Okay? So the advantage of this approach is that it combines two very well-known, well-studied techniques, SAT and ILP. But in practice, what happens is that you end up having to solve an exponential number of integer programs. So in the worst case, of course, one would have to enumerate all possible truth assignments to the SAT problem, and then each truth assignment corresponds to an integer program, right? And so integer program itself is quite hard to solve. So you have an exponential number of ILPs. And in practice too, I've observed that this exponential behavior does come up. Okay, so our approach is different. What we want to do is leverage the fact that this problem is an NP. So if there's any solution at all, then there better be one in the box. Okay, so it's sufficient to confine your search within the box of size D around the origin. So here's how our algorithm works. There are 3 steps. First, we calculate the solution bound D. Once we have that, we encode each integer variable with enough bits to represent any value inside that box.
Who showed the result of the bound D?
I'll come to that in the next slide. Okay. So we encode each integer variable with enough Boolean variables to express any values in that box, and then once integers have been replaced by Booleans, we can transform arithmetic operators to arithmetic circuits and the whole problem to a SAT problem. And then we run the SAT solver on it. The nice thing about this approach, in theory, is that it's a polynomial size translated to SAT because log D is polynomial input size, and it's also doable in polynomial time. But of course, the questions are we're translating to SAT here, so it's only useful if the SAT solver is solvable in practice, and that in turn depends upon the fact about the question of how large this bound D is. Okay, so here's an expression for D that was given by Papadimitriou, and all the other expressions are of the same order. So before I read that formula in yellow, let me say what the symbols mean. So M is the number of linear constraints, number of inequalities. N is the number of variables. B max is the largest constant in absolute value occurring in any of the constraints, and A max is the largest coefficient of any variable in absolute value. So given these definitions, let's go back and look at that expression on the top. It's the product of 3 terms. The first is a linear term in N and M. The middle term is B max, which is exponential in the number of bits needed to represent B max. But this expression is dominated by the last term, in which is an exponential term. The exponent is linear in M, the number of constraints, and the base is also linear in M if you treat A max as a constant. Okay, so D is really omega M to the M, and for any reasonably sized problem, M is of the order of 100 or so. So we're talking D is 100 to the 100. It's a huge box around the origin. So let's take a little example and see how large D can get. So here's a little circuit over linear constraints. there are 3 constraints, so m is 3. There are 4 variables, x1 to x4, so n is 4. Bmax is 10 from this term here, and Amax is 2 from that coefficient. And so if I calculate D for this little formula, it's of the order of 700 million, just for this trivial example. Okay, so it seems like, why would you want to go and do an enumerative search over this problem of size around this bounding box?
But you,
yeah.
Don't you get to take the log of it?
Get the log of it, but the log is still 20 something here, right? So I mean, this is like a really small formula, and you could just enumerate the terms.
For each x1, x2, x3.
Yeah, 20 bits for each x1, x2, x3, x4. So it's really overkill for this little problem, if you think about it, right? And for bigger problems, m would only get larger, and n would get larger, and the bound would get larger. All right? So it's a very conservative bound. That's the main message. But in fact, this is what we did. Okay, so I'll tell you how we did it. First, our solution is not to use that bound. Instead, to observe that most linear constraints in software are sparse. And what I did was to formalize what this means in terms of additional parameters to measure that sparseness. So I'm going to state the main theoretical result, which is the solution bound D, which is re-derived using these new parameters. And then I'll describe the implementation that and show that it gets even over 100x speed up over other decision procedures. Okay, so let's start with the main observation. I started this work about 2 years ago. I was just looking at problems generated from buffer overrun checks, turning that into a constraint solving problem. And what I realized was that constraints tend to have 2 characteristics from constraints from software analysis. First, most of them tend to be difference constraints, which is 2 variable inequalities of the form xi minus xj greater than or equal to a constant, or a single variable inequality that bounds a variable from above or below. Okay? And even if all of them aren't difference constraints, the ones that are not tend to be quite sparse. That is, they mention just a few variables per inequality. So then I went out and solicited examples from a bunch of verification projects. And for each such project, I got a set of formulas. So the middle column gives some statistics about these formulas. So the second one here says that for each project, I computed for each formula the fraction of constraints that were not difference constraints, took the max over all the formulas in that set, and that's the number in this column. Okay, so it's a really small number for each of those projects. And furthermore, if I did the same thing, except I instead measured the number of variables appearing in each constraint, and that's a very small constant. Okay, so so definitely there is this sparse structure that we should exploit, and I know that some similar observations have been made in the past, like in the ESC Java project, in the simplified tech report, and by Pratt way back in '77, but no one has really formally exploited this property. So that's what we did. I defined 2 new parameters to measure what sparseness means. So K stands for the number of constraints that are not difference constraints, and W stands for the number of variables per constraint at most. And then we add these parameters to the 4 that we already have, M, N, and Bmax and Amax. Okay, so I now have 6 parameters with which to measure input size. And our main theorem is that the solution bound D is given by this expression in yellow, and I'll come back to it in a second. And let me just do that by comparing it with the previous bound. Okay? So both of these expressions have a common term, Bmax. Ours has an order n square term up front. This is linear n and m. But look at the last exponential term. What I've done is to eliminate the linear dependence on m by a linear dependence on k, the number of constraints that are not difference constraints, and in general k is much smaller than m. And secondly, the linear dependence of m in the base has been replaced by 1 on w. Okay? And if you recall from the previous slide, w is the max number of variables per constraint, which is at most 6 in those examples. Okay? So this, in practice, it turns out to be a fairly significant reduction in the size of the bound. So let's look at the little example that we had earlier and recompute D for this. Shivendu.
Could you go back to the last slide? Yeah, so the fraction of non-difference doesn't really matter. It's the absolute value that matters, right?
Yes, so that's, well, there are two different things here. One is what I observed, which led me to study this problem further, and this is what I got. Okay. And so maybe there's some way of exploiting the fraction also.
Sorry, I didn't put all
Shuvendu asked, so what I have here is the number of non-difference constraints.
Yes, right.
The statistic I showed in the previous slide was a fraction of constraints that were not difference constraints. Okay, and those two things are different in general, right? But
what were the absolute numbers?
What's that?
You had the list of the fraction. What were the absolute numbers for the previous? Were they in the hundreds or thousands?
Well, so K was of the order of 10 or less.
10 or less.
A lot of them, and M was of the order of 1,000, right? Or even less than that, or even more than that. And so N is of the order of a few hundreds. Yeah.
Is it because most of the projects that you cite typically handle control dominated properties, right? And they typically ignore data related properties. And is that
Well, but then I think it's more a characteristic of the kind of software. Or most of them are about system software, and you don't have a lot of fancy computation going on there, right? Like, so if I had scientific, if I had scientific computing software, like for instance, doing some floating point arithmetic or even signal processing kernels, right? Then there I would I probably have more complicated linear constraints than I intend to have here. Most of the examples there, when I went back and talked to the people who generated those formulas, they said it's probably because what's happening there is a lot of copying and moving data around, but you don't actually do very much with the data. Okay, so let's go back to the little example here. And in this example, K is 1, which is this constraint. It's a not difference constraint, and W is 3, also from that one. And so if I calculate D, it's of the order of 1,000. So still somewhat large, but a couple of orders of magnitude smaller than the previous bound. Okay, so now I'm going to walk you through the proof of how we get this bound. Okay, and this proof operates in 3 steps. First, it's based on a previous result for integer linear programming by 3 mathematicians, Boros, Strebig, and Flahive. So I'll state that result. And then secondly, I'll say how we re-express that result in terms of the new parameters, K and W, in addition to the others. And that's really the main step of the proof. And then the third step is to generalize the bound from working for integer linear programs to working for arbitrary Boolean combinations of linear constraints. So let me start with some standard ILP notation. I'm going to think of a system of constraints that has to be solved in standard form. So AX equals B, AX non-negative. And so the parameters can be viewed thus. M is the number of rows in this matrix, 1 for each constraint. N is the number of columns, 1 for each variable. A max is the maximum coefficient of this matrix in absolute value. And B max is the maximum constant term on the right hand side in absolute value. So here's the result that we build upon. The solution bound D is given by an expression n plus 2 times delta, where delta is the largest subdeterminant of the combined constraint matrix AB, okay, in absolute value. So what that means is that you have to pick a square submatrix, some arbitrary square submatrix of this overall matrix, say the rows and columns highlighted in green, put it together, compute its determinant, take the absolute value, do this for all possible square submatrices of this matrix, and take the max, and that's delta. Of course, we just can't do what I said because there are exponentially many subdeterminants of this matrix. So you can't enumerate them. So what we did instead is to ask the question, how large can this determinant get for an arbitrary matrix? But in fact, we don't want to look at an entirely arbitrary matrix. We want to look at a matrix that has this sparse structure I just talked about. So what that means is that I can view the matrix as having the top k rows corresponding to non-difference constraints, and I can permute the rows such that all the bottom rows correspond to the difference constraints. And so k is quite small compared to m. And if I look at any given row in the top part, it has at most w non-zeros. And any row in the bottom part, of course, has at most 2 non-zeros because it's a difference constraint. Okay, so that's the structure we want to exploit. So let me derive the bound delta for the simple case where k equals 0. So there are all the constraints are difference constraints. So to remind you, difference constraints have the form that I've just written on the top of the slide. And so what that means in terms of matrix structure is that for each row, either there's only one non-zero, and that's a 1 or a -1, or there are two non-zeros, 1 + 1 and 1 - 1. So it turns out that the left-hand side of the matrix has a very useful property. It's called total unimodularity, which means that any subdeterminant of this matrix is either 0, -1, or +1. So if the subdeterminant is from the left-hand side, that's neat because we know that that determinant has to be at most 1. So what happens if it includes the last column? Well, using high school algebra, let's just expand the determinant on the last column. So we can do that by taking B1 and multiplying it by a subdeterminant from the left, minus B2 times something from the left, and so on. So in the worst case, what's going to happen is the determinant in green is going to be bounded by the sum of the BI's in absolute value. Okay, and the number of such BI's that are added up is at most the dimensions of any square submatrix, which is the minimum of the dimensions of the overall matrix. Okay, so that gives us a bound on delta. It's at most B max times minimum of n plus 1 and n. Okay, so let's look at the case for arbitrary k. So here's some submatrix of the original matrix, and it has less than or equal to k rows that correspond to non-difference constraints, and the diamonds represent the non-zeros. And in any given row, you have at most w non-zeros. And so if I look at a subdeterminant from the left-hand side, say the one outlined in yellow, then the value of the subdeterminant can be expressed as the sum of many terms if you just expand along the top rows. Now every such term is obtained by picking one element from each of the top k rows, one non-zero element, okay, say those 3, and then multiplying by determinant from the bottom. Okay, and the overall determinant is going to be the sum of many such terms. Okay. So if you look at any given term here, any of these entries is at most a max. There are at most k of them, so the product of those entries is at most a max to the k times something from the bottom, which is at most 1. So so each term is at most a max to the k, and the number of such terms that you would sum together to get the determinant value is at most w to the k, because the way you can generate each term is picking one unique element from one of the top k rows. Okay? So you could do that at most w to the k ways. Yeah?
Why don't you get the determinants that involve both the first and second row?
What's the question again?
The question is why can't I have a subdeterminant that involves both the first and the second row?
You could, I mean, this subdeterminant does involve the first and second row. So
I thought you said that you were considering subdeterminants where you consider one of the first 3 rows and then some subdeterminant from the bottom part.
No, so I'm assuming this matrix is some submatrix of the overall matrix, right? And then I'm just looking at some determinant on the right-hand side, some square submatrix, although this may not look square. But and so for this matrix, I've permuted the rows such that the top rows are non-difference constraints, and then the way I calculate the determinant value is to pick one non-zero from each of the top rows and multiply them together, and then multiply that by the bottom. Okay. But of course you could in picking this overall submatrix, you may leave out some of the top k or even the bottom rows. Okay, so so the determinant of the matrix highlighted in yellow is going to be at most a max to the k times w to the k. If the determinant also included the last column, then I'm going to have to end up multiplying each, in the worst case, multiplying each such exponential term with a bi. Okay, and so I'm not going to describe all the math, but basically the reasoning is the same as the previous slide, and we'd end up with an upper bound on delta that's given by this expression here. Okay. So anyways, so the summary is that on the previous slide, we had a bound that works for integer linear programs on delta. And then we have the result by Boros, Trading, and Flahive. And so putting those together and making a standard assumption, we'd get the bound on D to be given by the expression I talked about earlier. Okay, so that's the bound for integer linear programming. And so now what happens if we have an arbitrary Boolean combination of linear constraints? Now for the sake of the proof, I can view this formula phi as being in disjunctive normal form. And so that's the OR of it's an OR of ANDs where each phi I is an AND of linear constraints. A satisfying assignment to phi must satisfy some phi I, right? And so each phi I is an AND of constraints. You can view it as an integer linear program whose parameters, that is the values of m, n, and so on, are bounded by the values of the parameters of the original formula. So if I can bound the solutions, if I can find a bound that works for an arbitrary phi I, you can find a bound that bound works for phi as well. And so basically the same bound that I had in the previous slide works for arbitrary Boolean combinations as well. Okay, so that's the sketch of the proof. So let me now describe some experimental results. So there are two main approaches to solving quantifier-free Presburger. The first is the ILP plus SAT approach that I talked about earlier in this talk. But there is another approach based on automata theory. So let me just say a little bit about how that works. So the idea here is that a solution to the formula can be viewed as taking the solutions to all the integer variables. For each one of them, view them in some binary notation like 2's complement, and take all the 2's complement representations and stick them together, and that's a string that's accepted by this automaton. And so if you build up an automaton and its language is empty, we know that there are no solutions and therefore the formula is unsatisfiable. Now it turns out that these automata-based methods they're quite powerful. They can handle Presburger arithmetic with quantifiers as well. But the automata sizes tends to grow exponentially with the parameters of the input, like m and n, for instance. Okay, so what we did was to implement the finite instantiation procedure in the Euclid system that I talked about earlier, and we used the zeta SAT solver. We compare against CBC-Lite, the latest version of this prover that's been released from Stanford, which also uses the zeta SAT solver at its core. And we compare with the automata-based solver Lash from Belgium. The benchmarks were from the software verification projects that I cited earlier. And so the number of variables of the order of a few hundred, the number of constraints of the order of a few thousand. So here are the experimental results comparing with CBC-Lite. The runtime for Euclid is on the x-axis, and the runtime for CBC-Lite is on the y-axis. And it's a log-log plot. So points above the red line are those on which y is greater than x, so Euclid is faster. And so the main points in this slide is that the runtime for Euclid and all these benchmarks is of the order of a minute. There's a significant speed up we can get. So there are benchmarks on which CBC-Lite didn't finish within an hour, and our solver finished within just a few seconds. The automata-based solver didn't finish on any of these benchmarks within the time limit. Okay, so here's a class of examples from software analysis on which we can really exploit the sparse structure and generate a huge speed up compared to other state-of-the-art procedures. Okay, so let me summarize. The main points from this part of the talk was that linear constraints of software tend to be sparse in my study. I derived a solution bound D based on the new parameters that characterize the sparseness, and a decision procedure based on these on this result can get a large speed up over other procedures. Yeah.
Do you have an idea of how Simplify performs in these benchmarks?
I didn't run Simplify on these benchmarks, but Simplify doesn't have integer arithmetic, right? So in some sense, it's not a fair comparison.
Well, almost does. I mean,
it has a few heuristics.
Yeah.
But it's not a complete procedure.
Well,
Actually, I did find a problem with some, well, I don't know about simplify, but
It's not likely that you find an incompleteness problem, but in the formulas that you've tried, are they valid or not?
it's a mix of both.
It's mixed both.
Yeah, and the difficulty doesn't really depend on what it
try
is.
simplify it, and then I mean, if you get the discrepancy in one of the results, it could be because of such an incompleteness. But
Okay. Let me just say that some of the characteristics, so a lot of these benchmarks have a lot of Boolean structure, and it's similar to the benchmarks that the SRI folks used last year in their comparison of decision procedures that they presented at CAV. So in that study, they did use Simplify, and Simplify didn't do as well as CBC Lite or any other.
simplify is slow on the Booleans.
That's right. So I think that's the main problem that you would find even if you were to run Simplify on these benchmarks. Right. So if you didn't have interesting Boolean structure, then in fact this approach is a little of overkill, because you could just do case splitting, right, and run ILP on each of these, and that would do pretty well. So there's nothing to gain if it doesn't have much Boolean structure. Okay. So of course there's a question of what if this sparseness assumption doesn't hold, right? And we've addressed this in separate works. So we have an alternative approach that's based on iteratively increasing the size of the box D. You start with a small search within a small box. If you find a solution, well and good, you can stop. But if not, there's a systematic way of increasing it. So that also is a sound and complete decision procedure. Okay, so let me now finish up. I'll talk about some, I'll revisit the malware detection example as well as talk about some other applications. Okay. So we implemented a malware detector that has Euclid at its core as a decision procedure. And I'll just speak about the results that we obtained. So I did a comparison against commercial tools, and I'll talk about results against McAfee virus scan. And the comparison was with respect to 3 parameters. First, we found 21 variants of 3 worms that other people had written. So these were worms that are out in the wild, so to speak. And what we measured is the number of signatures needed for our detection system to catch all of them versus McAfee virus scan. The second parameter we measured is the detection rate for artificially obfuscated malware. So my co-authors generated 20 variants of each of these worms, and using fairly standard transformations like the one I talked about earlier, and we measure the detection rate, the accuracy of detection of our tool versus McAfee. And then third, of course, our approach is no good if it takes forever to run. So we measured the average runtime per program of our tool versus McAfee virus scan. So here's a table that summarizes the results. The first column is the features I talked about earlier. Middle column is our results, and the third is McAfee's results. So for 21 worms, our detector needed just 1 signature to catch all of them, whereas McAfee virus scan needed 13. In some cases, this was the entire binary. For the artificial obfuscated worms we generated, our detector had a 95% accuracy, whereas McAfee virus scan had got just 5% of those. But in terms of runtime, our tool is slower, a couple of order of magnitude slower. So our average runtime is of the order of 100 seconds, and McAfee virus scan is of the order of just a few seconds. So some of this could be offset by a smaller signature database. So we have fewer signatures to scan against. But there's still more work to speed up the decision procedure as well as the static analysis part.
So what is the 100 seconds actually measuring?
It's measuring the time that our tool takes to run on a given binary and report it as being malicious or not.
Single binary?
Single binary.
So what's the model that the McAfee virus scan would do that? How often would it do that? In practice.
How often?
How often is it scanning a binary like you're doing? How long is it taking that 5 seconds? Because is it whenever you download something on your system? Is it if it's a real-time monitor, or is this going across every binary on my disk?
So I think that's a separate. When you run it, is a separate issue. But what I'm measuring now is if you were to run McAfee virus scan, on your disk, it'll take an order of few seconds per binary.
Few
But
seconds per byte seems high, I guess, because it typically, well, you know.
so this is for,
yeah.
for the test set that we used. So there's details of that in the paper, and I can tell you more about that later if you want. So the programs are of the order of a few hundred KB. Yeah, around
The binaries.
Yeah, the binaries. Okay. So let me just mention a few other things I've done, and if you're interested in any of these, I can talk to you about this later. So there's more work that I've done on decision procedures in general. Let me just mention one piece of work that I did on using machine learning. So the idea here is that there's often not just one way of translating the SAT, but many ways. And in particular, you can decompose the original problem into sub-problems and use different encoding algorithms on the sub-problems. And so in practice, if there's a user of my tool, it would be just to get optimal performance out of the tool, it'll be a nightmare just to figure out what switches to set. And so we decided to automate all of that using machine learning from past examples, and that worked really well. I've explored a whole bunch of other applications. So for one of them in software is finding format string exploits. So what I mean by this is that it's a test generator for the class of security vulnerabilities called format string vulnerabilities. So if there is a potential vulnerability, we would generate a test case, a string that exercises that vulnerability. Yeah.
So I'm still thinking about what you just said now.
Yeah.
So the learning is to just guess the options to your algorithm.
That's right.
Okay.
Yeah.
How many options were there?
This work is just 2 options, but there are many sub-problems. So, I mean, if there was only one problem to decide, you could run both and see which one to use. But the idea here is that suppose let me give you an analogy. Suppose I wanted to solve a system of linear constraints, saying using Gaussian elimination or something, right? Then what I could do is, if this system was really huge, I could partition it into the matrix into block diagonal form and solve each subsystem separately, right? And then there are more sophisticated methods of doing that as well, even if the constraints were shared. It's the same analogy applied now to arbitrary Boolean combinations. You can decompose the original problem into sub-problems and figure out different ways of encoding and solving each one. Okay, so this is basically, you can view it as test generation applied to format string vulnerabilities. But at its core, it's using the decision procedure to come up with counterexamples and then turning them into test cases. So I guess model-based testing is probably the category this falls in. The other work I've done in hardware is modeling and verifying self-timed or asynchronous circuits, which I mentioned earlier. The sort of algorithmic work here is to do model checking of a class of automata called timed automata using the same SAT-based or BDD-based techniques. And I think in software, this work, although it's been applied to circuits, it's applicable to any system that operate under timing assumptions. So embedded systems do operate under real-time constraints, and some distributed systems also have interesting timing assumptions built into them.
So what do you use to handle the timing assumptions? Is that again Presburger arithmetic, or what is it?
So for the case of circuits, we actually model them as real values. So it's real linear arithmetic. Okay. And then both quantifier and quantifier-free, because you have to deal with quantifier elimination in doing the image computation for model checking.
So have you done similar work in real arithmetic constraints?
Yes. Yeah. Yeah. So I talked in this talk. I just spoke about the integer linear arithmetic part, but there's a class of similar techniques, not quite the same, but that based on translating to SAT.
Which you have developed?
Yes. Okay, so let me finish up by describing some directions for future work. Okay, so I think the architecture of translating to SAT has worked pretty well, but in general, in software analysis, one often tends to use a decision procedure as an oracle. So send us a sequence of queries to it, and Simplify is pretty good at handling this kind of sequence of queries. And so I'd like to do something similar in the case of Euclid. So given a sequence of similar input formulas, what the system would do is combine an incremental SAT solver with an incremental Boolean encoding algorithm so that we can reuse work that's been done in the past. But then there's other work to be done as well. So for instance, one question is what logics can we extend this translation to SAT approach to, in particular looking at heap data structures. I found that the SAT instances that are generated are really easy to solve, and so it's obviously because there is some structure to them. And so you can, in some cases, I've been able to formalize what the structure means and show why the SAT solver is this fast.
Can I ask you a question?
Yep.
Do you know, do you have an idea of what kind of extension to your logic would sort of solve the heap problem? It's not sort of immediately clear to me that by extending your logic in some way, get at it.
What do you want to do with the heap? I mean, you already handle arrays.
Right.
So unless you want to handle transitivity in the heap, then you've got what you need.
Right. But then, so handling transitivity is what I had in mind. But of course, we can't. The problem in general would then become undecidable, right? If I had transitive closure built in, right? So so then it would be a semi-decision procedure. And I'm thinking about approaches along the lines of Alloy that was built at MIT, where you choose instead of calculating a bound that's for which the procedure is sound incomplete, you just choose one that's small enough, large enough, and then you just explore all counterexamples within that bound.
Well, when you say arrays, he's got fixed size arrays.
No, you can have arbitrary size arrays.
But you have dynamic sized arrays.
We don't have dynamic sized
No,
arrays,
that's what
but
I mean.
you
But
could.
they have an infinite number, an arbitrary number of elements.
Yeah, but it's fixed to a constant up front, so it doesn't feel.
No, it's not fixed for a function up front. It's extensible.
Or it's an extensible.
That's right.
And so you handle extensible arrays already.
Yes.
So it's not quite clear to me how you do that.
I can tell you about that later if you want. Yeah. Okay. The other question to be answered is how do you generate a proof from this? This approach of translation to SAT is quite different from the CBC Lite or other approaches which have which can be generalized to generate proofs. But here, using the encoding I talked about in this talk, it's not quite clear. But anyway, that's work. That's direction for future work. Let me speak a bit about applications. I think the general area of software security has a lot of applications that we can throw decision procedures at. And the main area I'd like to look at is analyzing properties that are not just control dependent, but also have a lot of data dependency. One example of this is information flow. So the properties have the form of untrusted data flowing to trusted locations, or you want to check if secure data can flow to insecure locations. And currently there are type-based analyses for this problem. But I think theorem proving can increase the precision of these analyses if it can be made scalable enough. And I'd like to explore using the procedures I've built in that domain. The second example is something I talked about in this talk, which is malware detection. And so clearly, there's more to be done in scaling up this to larger binaries. There's also the question of improving its resilience to new obfuscations. So there's more work to be done there as well. And then there's this somewhat intriguing area that I've started working on with some people at CMU. The idea they want to do is improve the heterogeneity of software, so to speak, by morphing code without changing its functionality. So this general idea is it's similar to the malware detection example, except the good guys want to morph their code. And it's also similar to the translation validation problem. So I think there's scope of throwing theorem proving at this problem as well in making sure that you don't change functionality.
So
Yep.
along those lines, are you familiar with the work at Dexter on the project Denali, which is a super optimized?
Yes.
Yeah. So is that similar, or is there a significant difference?
I think it's similar, but I mean, sure, it is similar.
Okay.
You mean to what? To change?
Well, the idea is that if you morph, you morph the code. If you morph it into the most optimal form, and that's not super.
It's the same thing as the problem with optimizing compilers, right? You want to check that the transformation you made is preserved correct.
Right.
But what Denali does is it tries to find that optimal sequence. But
Right.
Sanjay is trying to study here is just checking if it's the same thing.
Right.
But actually, the last one could be thought of as a code synthesis problem, as they actually each time morphing to something else. The difference with Denali might be Denali has had one notion of optimality.
Right. All you have to do is a random generator that generates arbitrary configurations, and then a checker to see if it's the fastest, or some kind of evaluation procedure, right? But if you have
so that was the inspiration of Denali.
Right.
Okay. Okay. So these are so the last two slides are topics which I have some idea about, but this is what I'm going to talk about is more long term, and I don't quite know specific projects on this yet. So I've been looking so far at design time or static techniques, but of course what I'd like to do is try to look at runtime methods as well for error detection recovery. And so there's scope on, just as there's been work here at Microsoft on taking information about unverified properties and modeling assumptions and maybe synthesizing runtime monitors to detect correct errors. And at the same time, one can do specification mining by looking at runtime traces. So that's something I'd like to explore in the future. And then what we really need ultimately is some better metrics of reliability. And so there's this class of algorithms that are used in AI called anytime algorithms, where you can run the algorithm for a while and then stop it, and depending on if you run it longer, you get a more optimal result. And I think that's something like that needs to be developed in verification and static analysis. But of course, in order to do that, you need a good optimal function that you want to optimize, right? So you really need metrics. So these are things that I would like to start working on, but don't have the answers to. Okay, so let me finish up by acknowledging my co-authors and funding sources, and that's the end of my talk. I'll be glad to take questions now.
More questions? Thanks very much.
Thanks.
Yeah, actually, just cosmetic. That's good. I gotta go use the bathroom.
Okay, I was going to keep my laptop.
Okay.